Section 9.3 Phasors. Phasor is a very important concept which can be used to solve the sinusoid circuit. A phasor is a complex number that represents the amplitude and the phase of a sinusoid. Because the phasor is a complex number, so we can use complex number to calculate phasor. And a phasor can be represented in one of the following three forms. The first form is rectangular. Z equals x plus jy equals r multiplied by cosine phi plus j sine phi, where j is the imaginary unit. And you can find this complex number or this phasor in the graph. And you can find the real axis and the imaginary axis. X means the value of real part, and y means the value of the imaginary part. The second form is polar. Z equals r angle phi. The third form is exponential. Z equals r multiplied by e to the j phi power. Well, those three forms can be transformed between each other. But you should know r is the modulus of the complex number, and you can calculate r like this. R equals the root square of x squared plus y squared. And phi is the angle, and you can calculate phi like this. Phi equals arctangent y over x. Because phasors are complex numbers, so you can calculate phasors just like complex number. So we write the mathematical operation of complex number below. And suppose we have z, z1 and z2. And we can calculate the sum and the subtraction of z1 and z2 like this. We just add the real part together and add the imaginary part together. And we can get the multiplication like this. Z1 plus Z2 equals R1 multiplied by R2 angle phi 1 plus phi 2. As you can see, we just multiply the modulus together and add the angle together. The fourth operation is division. Z1 divided by Z2 equals R1 over R2 angle phi 1 minus phi 2, which means we can divide R1 by R2, and we can subtract phi 1 by phi 2. The fifth operation is reciprocal. 1 over z equals the reciprocal of r angle minus phi. The sixth operation is square root. The square root of z equals the square root of r angle phi over 2. The last operation is complex conjugate. The conjugate of z equals x minus jy equals r angle minus phi equals r multiplied by e to the minus j phi power. However, you should know that phasor is rotating. For example, if we draw a phasor V which representing the voltage and a current I which representing the current in the graph, and both V and I is rotating in the counterclockwise direction. However, you will find the voltage V is leading the current I. We can transform the polar form and the rectangular form of the phasor, e to the positive or negative j phi equals cosine phi plus or minus j sin phi. So the real part is cosine phi and the imaginary part is sin phi. So we can write a sinusoid Vt like this. Vt equals Vm multiplied by cosine omega t plus phi equals the real part of Vm multiplied by e to the j omega t plus phi. So what is the relationship between a sinusoid and a phasor? Actually, the sinusoid is the real part of a phasor multiplied by another phasor, which means Vt equals the real part of Vm multiplied by j phi multiplied by j omega t, where e to the j omega t is the rotating factor. And then we define the phasor Ve as Vm multiplied by e to the j phi power. So the sinusoid Vt equals the real part of V multiplied by e to the j omega t. So the phasor V equals Vm multiplied by e to the j phi power equals Vm phi. Actually, the phasor transforms a sinusoid from the time domain to the phasor domain. A sinusoid like this, Vt equals Vm cosine omega t plus phi, is in time domain. And a phasor V equals Vm angle phi is in phasor domain or frequency domain. Amplitude and phase difference are two principal constants in the study of the voltage and the current sinusoids. And phasor will be defined from the cosine function in all our preceding study. If a voltage and a current expression is in the form of a sine, it will be changed to a cosine by subtracting from the phase. So from now, we're going to use the phasor to represent the sinusoids and to solve the circuit using phasors. You can find the relationship between phasor and the sinusoids inside this table. If a sinusoid is Vm multiplied by cosine omega t plus phi, and the corresponding phasor is Vm angle phi. However, if the sinusoid is Vm sine omega t plus phi, you need to transform sine into cosine and then get the corresponding phasor, which means the phasor equals Vm angle phi minus 90 degree. Okay, those two are the phasors for the voltage. For the currents, the situation are just the same. If the sinusoid is Im cosine omega t plus theta, the corresponding phasor is Im angle theta. If the sinusoid is Im sine omega t plus theta, the corresponding phasor should be Im angle theta minus 90 degree. Okay, now what are the differences between Vt and phasor V? Okay, Vt is instantaneous and time domain representation of a sinusoid value. However, the phasor V is the frequency of phasor domain representation. Vt is time dependent while Phasor V is not. Vt is always real, with no complex term. However, the Phasor V is generally complex. You should notice that phasor analysis applies only when frequency is constant, when it is applied to two or more sinusoid signals, only if they have the same frequency. Why do we use the phasors to analyze the sinusoid circuit? Because there are very important advantages when we use phasors. So the relationship between differential integral operation in phasors are listed below. So if the sinusoid is Vt and the corresponding phasor is V, and then the differential of V corresponding j omega V, and the integral of V corresponding V over j omega. So you can find the calculation with phasor is quite easier with respecting the time domain or the sinusoid value. This is the end of this section.